Qlearning is a model-free reinforcement learning technique. Specifically, Qlearning can be used to find an optimal action selection policy for any given Markov decision process. It works by learning an action value function that ultimately gives the expected utility of taking a given action in a given state and following the optimal policy thereafter. A policy is a rule that the agent follows in selecting actions, given the state it is in. When such an action value function is learned, the optimal policy can be constructed by simply selecting the action with the highest value in each state. One of the strengths of Qlearning is that it is able to compare the expected utility of the available actions without requiring a model of the environment. Additionally, Qlearning can handle problems with stochastic transitions and rewards, without requiring any adaptations. It has been proven that for any finite MDP, Qlearning eventually finds an optimal policy, in the sense that the expected value of the total reward return over all successive steps, starting from the current state, is the maximum achievable. Algorithm: the problem model consists of an agent, states S and a set of actions per state A. By performing an action, the agent can move from state to state. Executing an action in a specific state provides the agent with a reward. The goal of the agent is to maximize its total reward. It does this by learning which action is optimal for each state. The action that is optimal for each state is the action that is the highest long-term reward. This reward is a weighted sum of the expectation values of the rewards of all future steps starting from the current state, where the weight for a step from a state steps into the future is calculated as. Here is a number between 0 and 1 called a discount factor and trades off the importance of sooner versus later rewards as the likelihood to succeed at every step. The algorithm therefore has a function that calculates the quantity of a state-action combination. Before learning has started, Q returns an fixed value, chosen by the designer. Then, each time the agent selects an action, and observes a reward and a new state that may depend on both the previous state and the selected action, Q is updated. The core of the algorithm is a simple value iteration update. It assumes the old value and makes a correction based on the new information. Where is the reward observed after performing in, and where is the learning rate? An episode of the algorithm ends when state is a final state. However, Qlearning can also learn in non-episodic tasks. If the discount factor is lower than 1, the action values are finite even if the problem can contain infinite loops. Note that for all final states, is never updated and thus retains its initial value. In most cases, can be taken to be equal to 0. Influence of variables on the algorithm. Learning rate equals. The learning rate determines to what extent the newly acquired information will override the old information. A factor of 0 will make the agent not learn anything, while a factor of 1 would make the agent consider only the most recent information. In fully deterministic environments, a learning rate of is optimal. When the problem is stochastic, the algorithm still converges under some technical conditions on the learning rate, that require it to decrease to 0. In practice, often a constant learning rate is used, such as for all. Discount factor equals, the discount factor I cubed determines the importance of future rewards. A factor of 0 will make the agent myopic by only considering current rewards, while a factor approaching 1 will make it strive for a long-term high reward. If the discount factor meets or exceeds 1, the action values may diverge. For I cubed equals 1, without a terminal state, or if the agent never reaches 1, all environment histories will be infinitely long, and utilities with additive, undiscounted rewards will generally be infinite. Initial conditions equals, since Qlearning is an iterative algorithm, it implicitly assumes an initial condition before the first update occurs. A high initial value, also known as optimistic initial conditions, can encourage exploration. No matter what action will take place, the update rule will cause it to have lower values than the other alternative, thus increasing their choice probability. Recently, it was suggested that the first reward could be used to reset the initial conditions. According to this idea, the first time an action is taken the reward is used to set the value of This will allow immediate learning in case of fixed deterministic rewards. Surprisingly, this resetting of initial conditions approach seems to be consistent with human behavior in repeated binary choice experiments. Implementation: Qlearning at its simplest uses tables to store data. This very quickly loses viability with increasing levels of complexity of the system it is monitoring controlling. One answer to this problem is to use an artificial neural network as a function approximator, as demonstrated by Tesaro in his backgammon-playing temporal difference learning research. More generally, Qlearning can be combined with function approximation. This makes it possible to apply the algorithm to larger problems, even when the state space is continuous, and therefore infinitely large. Additionally, it may speed up learning in finite problems, due to the fact that the algorithm can generalize earlier experiences to previously unseen states. Early study: Qlearning was first introduced by Watkins in 1989. The convergence proof was presented later by Watkins and Dallin in 1992. Variants: delayed Qlearning is an alternative implementation of the online Qlearning algorithm, with probably approximately correct learning. Because the maximum approximated action value is used in the Qlearning update, in noisy environments Qlearning can sometimes overestimate the action's values, slowing the learning. A recent variant called double Qlearning was proposed to correct this. Greedy GQ is a variant of Qlearning to use in combination with function approximation. The advantage of greedy GQ is that convergence guarantees can be given even when function approximation is used to estimate the action values. Qlearning may suffer from slow rate of convergence, especially when the discount factor is close to 1. Speedy Qlearning, a new variant of Qlearning algorithm, deals with this problem and achieves a provably same rate of convergence as model-based methods such as value iteration. A recent application of Qlearning to deep learning, by Google DeepMind, titled Deep Reinforcement Learning, or Deep Q Networks, has been successful at playing some Atari 2600 games at expert human levels. Preliminary results were presented in 2014, with a paper published in February 2015 in Nature. See also, Reinforcement Learning, Temporal Difference Learning, SARSA, Iterated Prisoner's Dilemma, Game Theory, Fitted Q Iteration Algorithm. External links: Watkins, CJCH Learning from Delayed Rewards. PhD thesis, Cambridge University, Cambridge, England. Strill, Lee, Weyera, Langford, Littman. PAC Model Free Reinforcement Learning, Reinforcement Learning, An Introduction by Richard Sutton and Andrew S. Bartow, an online textbook. C6.5 Qlearning, Off-Policy TD Control. Pickle, a generic Java platform for reinforcement learning, Reinforcement Learning Maze, a demonstration of guiding an ant through a maze using Qlearning. Qlearning work by Gerald Tesaro. Qlearning work by Tesaro Cytosea link, Qlearning algorithm implemented in processing.org language, solution for the pole balancing problem with Q, lambda, /SARSA, lambda, and the Fourier basis in JavaScript. References: Reinforcement Learning, An Introduction. Richard Sutton and Andrew Bartow. MIT Press, 1998. Stuart J. Russell. Peter Norvig. Artificial Intelligence, A Modern Approach. Prentice Hall. Pages 649. ISBN 978-0136042594. http, abdocs cs Albertica Book Node 21 HTML, Steinart, H. Neyman, T. Lowenstein, Y. The Role of First Impression in Operant Learning. JEXP Psychol.Gen. 142, 476 €88 doi, 10.1037 per R0029550. PMID 22924882. Tesaro, Gerald. Temporal Difference Learning and TD Gammon. Communications of the ACM 38 doi, 10.1145/203330.203343. Retrieved February 8, 2010. Haddo van Hasselt. Reinforcement Learning in Continuous State and Action Spaces. In Reinforcement Learning, State of the Art, Springer, pages 207 to 251, 2012. Watkins, CJCH Learning from Delayed Rewards. Ph.D. Thesis, Cambridge University. Watkins and Dan, CJCH Qlearning Machine Learning, Alexander L. Strel, Li-Hong Lee, Eric Y. Oira, John Langford, and Michael L. Littman. PAC Model Free Reinforcement Learning. In Proc 22nd ICML 2006, pages 881 to 888, 2006. Van Hasselt, Haddo. Double Qlearning. Advances in Neural Information Processing Systems 23, 2613 to 2622. Hamid May, and Xabasepis Shalab Batnikar and Richard Sutton. Toward Off-Policy Learning Control with Function Approximation. In Proceedings of the 27th International Conference on Machine Learning, pages 719 to 726, 2010. Xabasepis The Asymptotic Convergence Rate of Qlearning. Advances in Neural Information Processing Systems 10, Denver, Colorado, USA, 1997. Shlaghi Azhar, Muhammad. Munoz, Remy. Arvamzadeh, Muhammad. Kaplan, Hilbert J. Speedy Qlearning. Advances in Neural Information Processing Systems 24, 2411 to 2419. Mni, Volodymyr. AL Human Level Control Through Deep Reinforcement Learning 518 pages 529 to 533.